She will tell us about the programmable fermionic quantum simulation using optical tweezer arrays.
Hi, everyone. First of all, I'd like to thank the organizers for putting on this workshop and inviting me to tell you a little bit of the progress done in Wasim Bakar's group at Princeton University. So I'll be telling you about programmable fermionic quantum simulation using a relatively newer platform, which is this optical tweezer array platform. So ultra-cold atoms loaded in optical tweezer arrays have become really popular in the last half-decade or so. And this was basically started by two pioneering experiments done respectively by the Brouwers group and the Luken group, where they loaded Rydberg atoms in these defect-free software programmable arrays. And there have been multiple breakthroughs among many groups around the world, for instance, building precise optical tweezer clocks for metrology, or demonstration of entangling operations for quantum computation. And what we're primarily interested in is simulation of quantum many-body systems. Just to give you a flavor of what's been done with this platform, with localized Rydberg atoms, they've been able to study beautiful spin physics, including interacting topological phases of matter with the SSH model, frustrated spin models, and even the appearance of the elusive quantum spin liquid phase with individual Rydbergs placed on links of a Kagome lattice. Everything I just showed you in the previous slide was done with localized atom, where they're basically frozen and the quantum statistics of the particle don't come into play. But there are a smaller class of experiments that are trying to study the interesting problem of itinerant systems, so where the particle being bosonic or fermionic does truly matter. So for bosons, this was pioneered by the group of Cindy Regal. Here you can see a demonstration of the Honglu-Mandel interference effect with bosonic rubidium in a double well system. And for fermions, this was pioneered by the group of Selm-Joachim at Heidelberg. You can see coherent Rabi oscillations between atoms hopping between two wells, and they've demonstrated entanglement in, I believe, up to a system of 3 tunnel-coupled tweezers. So naturally, we want to take this approach and scale it up to more and more particles, and we view this as a truly bottom-up approach to quantum simulation. Let me tell you about 3 potential targets that we might have. Number 1 is a lower entropy Fermi-Hubbard simulator for a 2D square lattice. As has been mentioned before, this is thought to be a minimal model for cuprate high TC superconductivity. We're also interested in studying 1D topological phases of matter. So I'll show you some preliminary results on the 1D interacting Su, Schrieffer, Heeger, Hubbard model. And finally, as an outlook, we'd like to probe exotic flat band geometries where interaction energies can completely dominate over kinetic energies, and you see exotic physics. All of this is really aided by our ability to dynamically control each individual lattice site, the geometry, the intensity, and the energy offset between each tweezer, sometimes in a dynamic fashion within one single experimental shot. Briefly, I'll mention one big challenge, I would say, facing the community. It's been touched upon before. The typical way to simulate Fermi-Hubbard systems with interferometric optical lattice has been it's produced really fruitful results, and we've learned a lot. But the next challenge, the next frontier, is to go down to colder and colder temperatures. So our cold atom systems are quite hot when compared to condensed matter systems, where they can routinely achieve 10 to the minus 4 T over TF. We are limited in our community to around 0.1, and that's because collisional evaporative cooling becomes more and more inefficient as you approach 0 temperature for fermions. This is not a fundamental issue, and many people are working to overcome this challenge. Nevertheless, so far, the state of the art for KBT has been roughly a quarter of the tunneling energy, which, if you look at the Fermi-Hubbard phase diagram in 2D, this has been enough to see mod insulators with antiferromagnetic correlations, with some amount of doping. People have seen the strange metal phase. However, the pseudo gap and whatever lies at the T equals 0, be it superconductivity or strike phase, these still are out of reach. So we decided to take a different approach, which is broadly termed quantum state engineering. And the general idea is that you start with a wave function, a low entropy product state that's experimentally easier for us to prepare. For instance, a band insulator of a single spin up plus down on one lattice site. And then you adiabatically evolve that into a correlated state. For instance, at half filling, this would be Mott insulator with AFM correlations. This was first proposed to be done with optical superlattices, and there's been really great experimental work in the group of Marcus Greiner using, I believe, a DMD. However, in the experimental work, the final step of evolving from the band insulator to the antiferromagnet introduced a certain amount of heating in the system, so it wasn't entirely adiabatic, and that precluded that particular experiment from achieving record low entropies. We decided to do this with a bit more flexibility afforded to us by the optical tweezer platform. Here's an experimental cartoon. Theorists can go to sleep right now. Basically, we generate the tweezer array in one dimension for now using an acousto-optic modulator. Each radio frequency tone generates a single lattice site, as shown in the bottom. And then we do all of our science in the tweezer array. And then for imaging, we load back into shorter periodicity optical lattice. We just call it our imaging lattice. And we perform site-resolved quantum gas microscopy. We collect the fluorescence image from each individual lattice site. And there we can reconstruct like single particle measurements like correlations. So to begin the experiment, we load a degenerate gas of fermionic lithium-6. It's a mixture of two hyperfine states. From the bulk degenerate gas, we turn on these very tight dimple, these small tweezers, which have a very high local Fermi temperature because the density is high. But then the overall temperature remains the same, so therefore we can really reduce T over TF. And we don't want to populate many vibrational levels. So with a combination of lowering each tweezer depth as well as spilling with a magnetic gradient, we can end up with lowest band populated only, or lowest vibrational state populated only. And this can be done with 97% single atom loading fidelity. This technique was pioneered by Selim Yokum's group. So how do we create this correlated state? Well, we start with a loading lattice, right now with 4 sites as pictured. This one we can prepare with very low entropy. With post-selection, we can even further reduce the entropy. Then we adiabatically turn on every intermediate site, ramping the detuning delta to 0 in a manner much slower than the single particle tunneling. And in the end, we hope to achieve the ground state of what we call our science lattice with on-site interaction U controlled by magnetic Feshbach resonance, and the single particle tunneling is set by both the distance between the tweezer sites as well as the depth of each tweezer site. So one key ingredient is single particle tunneling. And I have to say, one big downside of the tweezer platform compared to the interferometric lattice is single particle tunneling is really difficult to achieve because we don't get a homogeneous array for free. We have to work really hard to balance each tweezer to be the same potential energy as the other tweezers. We do this with a density balancing algorithm I'm not going to tell you about, but the proof that we have tunneling across the entire array is, of course, to do a quantum lock. So we initialize one atom on site 1, and then at time 0, we quench on the tunneling, and we see this textbook-like quantum walk going from site 1 to site 8 before it bounces back, and there is both decoherence and some uncontrolled disorder in the system, which is why the experiment does not look exactly like the theory. Nevertheless, this is how we calibrate our single particle tunneling. What we can do, which a typical interferometric lattice cannot, is to prepare staggered lattice geometry. For instance, alternating strong and weak tunnelings just by alternate the tweezer spacings. And we can, again, see the quantum lock, this time with a slightly different interference pattern. So I promised you that we were able to create correlated states, not just boring band insulators or single particle states. So we were able to create a Mott insulator at half filling, of course. And let me walk you through this plot. We all know that for highly repulsive interactions, doubles and holes are suppressed, so the singles fraction should reach nearly 100% in the infinite Heisenberg limit, whereas for the non-interacting case, u equals 0, you have exactly 50% chance to have a single on any given site just from counting statistics. And this is what we measure, very consistent with the theory. And the snapshot shows one single fluorescence image of a perfect Mott-insulating state, so not spin resolved in this instance. And even though the lattice looks disordered in the snapshot, the underlying science lattice is periodic and very uniform. It's just that when we load back into our imaging lattice, the image looks a little bit disordered because they're not one-to-one lying on top of each other. So to prove that we've created a kind of low entropy state, we have to measure antiferromagnetic correlations, which only appear as t approaches 0. So in this particular experiment, we were not able to image both spin states. Now we have that capability, but here we were only able to measure site-resolved spin-up correlators. We had to blow away the spin-down atoms. You see the experimental up-up correlator matrix, as well as theory. This theory has one free fit parameter, and that's the temperature of the system. And in 1D, as you may know, there's no long-range order of any kind. The correlations just die out exponentially. And because we have a finite size effect, the correlators will alternate sign and not really damp out to 0 even for the longest distance that we can measure. But we see signatures of what we would expect. The nearest neighbors are strongly negatively correlated. The next nearest neighbors are slightly positively correlated, so on and so forth. Yeah?
In this case, doublons are also blown away.
No. No.
So in this case, doublet will stay behind this one spin.
Yes, yes. But we did post-select on imaging for up atoms in this case, but these data are spin imbalanced because sometimes there could have been imperfections in the downspin population. So where does the entropy enter into our system? So there are two separate methods. Number one is we prepared an imperfect loading configuration. The band insulator I told you about, we would like to have 8 atoms, 4 plus 4. However, we have minor probability of a flaw as pictured. And if you just plug in the binomial probability, this corresponds to a loading entropy of roughly 0.1 kb per particle, which is still good. The bigger problem comes in our so-called adiabatic ramp, where if we start with the hole imperfection, this is a localized hole, which is not the ground state of the 4-site system. So when we turn on the 8 sites, we will, with high probability, not occupy the ground state of the 8-site system. So that's a big downfall of the system. The simulation shows that we would gain an entropy of 0.2 kb per particle just from having that localized hole in the beginning. So what do our data tell us? Like I mentioned, we fit our experimental spin-up correlator to theory from exact diagonalization with one free fit parameter, which is the temperature. As you can see, at low temperatures, the spin correlators are as strong as possible, and at high temperatures, they kind of wash out to 0. So we determined temperature of roughly 0.2 kb per particle, and this corresponds to a measured entropy of temperature of 0.2 of tunneling and a measured entropy of 0.26 kb per particle. So this is consistent with what we expected from the previous slide. This is also near state-of-the-art, or state-of-the-art, but for a very small system size and in 1D. We were not super happy with this. We wanted to push this, and one way to do it is with full spin post-selection, so keeping only perfect spin up and spin down configurations. We also wanted to scale this to 2 dimensions where things aren't always exactly solvable. So let me first talk about the technical upgrade. Scaling to 2D, on the face of it, there's a very big challenge. Most people who do tweezer arrays, they do it in the following way. They have 2 acousto-optic devices oriented 90 degrees from each other. One AOM generates the X tones, one AOM generates the Y tones. You have a Cartesian product grid. But the problem is you only have m plus n degrees of freedom. That's not enough to homogenize the array, which has m times n sites, if you go above 2 times 2, of course. So this would not work for an itinerant system, although it does work for the Rydberg experiments, right? So we pioneered a stroboscopic technique where we use time as an effective third dimension. Basically, we concatenate different one-dimensional chains, as shown here, and we repeat this very quickly compared to the tweezer trap frequencies. And so the atoms will experience some time average potential. That way, we have enough degrees of freedom to homogenize the array, and we can also make geometries which are pretty much impossible to make with conventional optical lattices. Two limitations on the strobe technique. I mentioned that the strobe rate has to be much faster than tweezer trap frequencies, otherwise the atoms will actually experience the blinking and be heated out of the potential. So we found empirically that we needed to strobe faster than around 300 kilohertz. Above that rate, our lifetimes are consistent with the non-strobe lifetime, which is in the red data point. And we were helped by our theory collaborators from Caden Hazard's group. They computed the flow K heating rates without any free-fitting parameters, and that agreed quite well with our data up to a small systematic. We also can't strobe too quickly because the AOM speed of sound is finite. And for fun, we can just show you what happens when you strobe too quickly. You get these, what I call fat tweezers. No one wants that. So another way to increase the lifetime in our sample is to do partial modulation. So you basically superimpose a completely static array on top of a strobed concatenated 1D array. You can only create Cartesian products this way, but this wins you a little bit in the tweezer ground state lifetime. So with this, we're able to load arbitrary geometries of up to 50 fermions, 25 in each spin component, and you can see a 5x5 square lattice on the left, a lead plaquette, a triangular ladder, as well as an octagonal ring. And so the top are single images of one spin component, and the bottom are averages of over 100 shots. Next, we wanted to reduce our entropy towards 0 through full spin post-selection. So to do this, we had to implement full spin charge readout with our quantum gas microscope. We did this through a bilayer trick, which has also been used in other groups. Here you see a single snapshot, simultaneous image of the spin-up population and the spin-down population. So 3x5 rectangular grid. Now let's plot the population matrix versus spin-up and spin-down number. So you see in this particular data set, which I believe we took over 700 images, roughly 12% of our images were perfectly filled with 15 plus 15 fermions. And if we threw away all the other data, that would correspond, of course, to a loading entropy of 0. If we were to tolerate one imperfection, for instance, keeping 14 plus 15, we would still only pay the price of roughly 0.1 kV per particle, which is not bad. With all of these ingredients, we managed to build a very basic building block of the 2D Fermi-Hubbard model, which is a 2x2 Hubbard plaquette. As before, we load a band insulator on sites 1 and 4. They're not tunnel coupled right away. Then we adiabatically turn on sites 3 and 2, thus going towards half filling. And we can measure now the SZSZ spin correlator. And we're at intermediate repulsive interactions. So what we can measure with our quantum gas microscope is the population of the microstates that are allowed. So you can think of this as the diagonals of the density matrix. And we perfectly post-selected to only keep shots with 2 upspins and 2 downspins. That corresponds to 36 allowed configurations. You see theory on the top, experiment on the bottom, and maybe not surprisingly, the 4 most allowed, or the 4 most common microstates are the Mott insulating states, with 1 atom per site. And our theory and data match exceedingly well with temperature, again, as the only free fitting parameter. But to our happy surprise, our temperature is so cold so as not to be sensitive in the spin-spin 2-point correlator anymore. So the SZ-SZ correlation kind of saturates below a specific temperature. So we were only able to put an upper bound of KBT to roughly a third of tunneling. However, our data are consistent even with 0. You can ask, why didn't we measure higher order spin correlators? We just took maybe 1,000 images to measure 3 or 4-point correlators. You, of course, need to take orders of magnitude more data. But that is probably where the temperature truly hides, in the higher order spin correlators. This temperature corresponded to an entropy range of at most 0.09 kb per particle, which is, we believe, a record in the field, although, of course, this is a very small system size. So our outlook is to, of course, scale this up to larger systems. We think that with the AOM technique, we can get to 50 fermions we've demonstrated, although not yet tunnel coupled. And we hope that we can keep the entropy low and still adiabatically evolve into ground states, even though the gaps do tend to get smaller and smaller as the system size increases. Switching gears, I want to tell you about our latest work on the fermionic Sue-Schrieffer-Heeger model. Also sometimes people call it the Sue-Schrieffer-Heeger-Hubbard model. So this is the SSH model is a textbook, one-dimensional model that hosts a symmetry-protected topological phase. In fact, it's one of the simplest topological models that you can write down. When you don't have any interactions, this model hosts 2 distinct topological phases, one trivial, one non-trivial. You can think of this as a dimerized chain where you stagger the tunneling. If you're in the trivial phase, that means your tunnelings are strong on the edges and the interior is staggered to be weak, strong, etc. There, you don't have any ground state degeneracies as shown in the energy level diagram. But if you stagger in the opposite way with the weak links on the edges, there you have a 4-fold ground state degeneracy, and you have degenerate edge states which give you this non-trivial Zach phase. And this is a distinct topological phase compared to the trivial orientation. So we implement this model also with on-site Hubbard interactions. I'd also like to point out similar work done previously by the Brouwers and Block groups. So we decided to perform a kind of cute measurement to characterize the long-distance spin entanglement in an SSH chain. So as a reminder, in the Heisenberg limit, the charge fluctuations are frozen out, and this can be thought of as an effective spin model with nearest neighbor antiferromagnetic interactions in the bulk, as I previously have shown. But the ground state of the topological phase is interesting because it actually hosts long-distance entanglement between the edge spins. If you're truly in the ground state, the edge spins should form a perfect Bell pair in the infinite U over T limit. Of course, we are not in the infinite U over T limit, so we have some admixture of the singlet Bell pair with antisymmetric correlations. So how do we characterize that? Well, we can measure spin-spin correlations in 2 independent bases, and that will put a bound on the amount of entanglement through the chain. So on the left, you see SZ-SE correlation measurements. On the right, we performed a global pi/2 spin flip, so that we're looking at SX-SX correlators. And in both cases, you see that in the bulk, there are nearest neighbor anticorrelations, as I've shown you before. But the novel thing now is that sites 1 and 8 on the edges are also anticorrelated. And we can use this entanglement metric called the concurrence, which is just a function of these correlators. As long as the concurrence is strictly positive, you have some degree of entanglement in the system. This is the experimental concurrence matrix. You see that these nearest neighbors are entangled, as well as the edge-to-edge. And our lower bound of 0.53 with our uncertainty of 0.02 indicates proof of edge entanglement. So to our knowledge, this is a demonstration of strong long-distance entanglement across the chain, mediated by purely on-site contact interactions. And this entanglement is roughly 10 micron in distance. Yeah? Okay. As an outlook, we would like to study pairing in frustrated and doped systems. For instance, if we were to generate a zigzag ladder and heavily spin and balance it and also hole dope it, this theory paper tells us that we should see binding between these spin-ons and these hole-ons with binding energy that scales with single particle tunneling rather than the exchange interaction, which is obviously much more favorable and we think should be achievable with our given temperatures. We're also interested in studying the triangular lattice with the possibility to see the spiral order of 120 degrees at high repulsive interaction. And maybe more interestingly, at intermediate U over T, people have suggested that this might host a quantum spin liquid phase. And with that, I would like to acknowledge the team. This work was done under the supervision of Wasim Bakr at Princeton and was carried out by grad students Ben, Max, Elmer, and undergrad Sanjay. I'd also like to acknowledge our theory collaborators for the flow K heating, Caden, Haotian, Eduardo. And if you're still here on Wednesday, please stay for Wasim's talk, Probing Site Result Correlations in a Spin System of Ultra-Cold Molecules. So, thank you for your attention.
Thank you very much for this very interesting talk. So please.
So the splitting of the lowest state between the two edges and the opposite bell pair should go exponentially down with distance, or?
Yes.
So the obvious question is, do you see basically that concurrence gets weaker if you make this thing longer or shorter?
Yes, we did this with a 4-site chain where the lowest gap is 0.2 of tunneling. We did this for the 8-site chain, as I've shown you here. Here we had to be colder than 2% of tunneling in order to see this. But yes, in the 4-site chain, the concurrence was stronger because the gap is larger, exactly as you say. We weren't able to push beyond 8. We tried 10, but we didn't really see anything.
It's also interesting that you absolutely have no entanglement between your weak links, right, in the bulk.
Yeah. I mean, this is a finite size effect. But there's also this thing called monogamy of entanglement, I guess. Like for bipartite entanglement, if 2 spins are very entangled, neither one of them can be entangled with a third.
It's just
spin.
It's just a picture. It's funny that you have the edges entangled, and in the middle, basically, the chain is broken, right?
Our chain is not broken. We always calibrate with the quantum lock, but even here, you see some staggering, right? Yeah.
What is the lifetime or heating rate starting from these super low entropy states?
The lifetime, let me see where So our lifetimes are several factors above our tunneling energies. So let's say 10 seconds compared to maybe 200 or 300 hertz tunneling energies. And these lifetimes are actually shorter. These are the lifetimes in the very deep tweezers where we load our initial band insulator. To go to the correlated state, we actually decrease the intensity of each well in order to allow for tunneling. So the spontaneous emission rate as well as the, I believe the flow K heating rate should also scale down. So I would say the lifetime is at minimum order 8 or 10 seconds.
So what are the numerical values of the heating rates approximately?
Well, Caden can probably answer better than me, but 10 seconds is, 0.1 hertz or so.
I didn't hear the question.
Oh.
But that's actually lifetime, right? That's not.
This is the ground state lifetime, not just the lifetime of trapping. Sorry, I wasn't clear. these data were taken by doing the magnetic spill, holding, and then doing a second magnetic spill. So we're only imaging atoms in the ground vibrational band. So if any atom had like got heated to V equals 2 or V equals 4, like they would have disappeared. Yeah.
When you talk about static configuration, you said that disorder was an issue. You had to compensate for it.
Yeah.
But you did not comment on disorder in the Strubas population. Is it less severe or is it more of an issue?
Oh no, every pattern that we strode, so every single time step, we have to basically change each radio frequency tone to make the disorder go away. So it is just as much of an issue in the strobe configuration as the static, but
not more. I mentioned it's more because somehow you have to use the same parameter. Just maybe.
no, actually, we change, like each of these 4 time steps, we're changing the tweezer parameters. So
They're completely independent.
yes, yes.
And so roughly, can you give us an idea? Should I think about disorder in sort of the bottom of the wells as the main source of disorder, and sort of, I don't know, like a local chemical potential? So how much does it vary from site to site?
Yes. So basically, we need the disorder delta, which is like a local chemical potential, to be smaller than roughly half the tunneling or a third of tunneling. Otherwise, it's completely disconnected.
And roughly what is it now?
So we cannot perform a good enough fit to know exactly the disorder from site to site. All we know is that our ability to do the quantum walk bounds the disorder maximally to like T/2 or something. But yeah, a big experimental challenge is that, this disorder may change on the several hour time scale. Like every time we balance the array, it's only good for data for like, at best, 8 hours, 10 hours, and then, the lab temperature drifts and we have to rebalance, so.
Back on the heating rate, so that number is a tweezer ground band number, right?
Yes.
There is also the question of does the inter-tweezer motion of the wave heat?
The intertweezer what?
Does the, like if you begin a temperature over tunneling of some value, does that heat any faster than the purely intra-tweezer motional states?
Intra.
Yeah.
It's like interband versus in-band.
So like that measurement you said was a deep tweezer.
Yeah.
But if you went to a shallower tweezer where there is tunneling among sites.
Oh, sure,
that thing
sure. This is not something that we've experimentally investigated to our knowledge, but I would just say that the trap frequencies will go down as root of the power, so we have to pick our strobe rates very wisely to always be in the limit where we're, for instance, over 10 times the strobe rate throughout our entire system. Yeah.
I was wondering if it was possible to maybe do pre-selection by imaging the doublons in the tweezers and non-destructively.
Yeah, that would be the dream. I think for us, we haven't really tried this because our imaging scheme, we load into a square optical lattice and do Raman sideband cooling, and this does not preserve the vibrational quanta of every atom. So it basically heats up to very high bands, and I don't believe that that's necessarily fundamental, but I think unless you had maybe an atom with some very narrow line transitions, like, then maybe it's possible, but for us, we haven't tried this.
But you don't need to have that many photons per atom to tell. you're not trying to figure out where exactly it is. You just need to see that the tweezers can be quite far apart, supposedly. You just blast it, you lose that atom, and you say, I'm not going to use that tweezer anymore.
Yeah, so theoretically, we could move the tweezers far apart, image in the tweezer, which we do not do, but it should be possible, and then move them back together. So far, when we've tried moving, we've seen a different heating effect, which could be that when we both strobe and move, sometimes the RF tones interfere with each other in funky ways, and we haven't experimentally perfected moving without heating.
So how about realizing small but doped systems adiabatically? Is that possible?
Yeah, that's something we're really interested in, because you could have as many empty sites initially and turn on additional sites. That's one way to do hole doping. That's
So there's no issues fundamentally that you see?
I mean, I guess it depends on precisely how you do it, but as long as you keep a gap that's like some fraction of tunneling and not much smaller, it should be possible.
One more technical question. So, for the strobing, you will hit at one point the limit because of your cycle, your duty cycle goes down if you make it longer, right, in one direction.
Yeah.
So, but there are also electro-optical modulators. Did you ever consider using one of the? I think they are 10 times faster or something like this, or even more.
Yeah. So let me
not modulators, deflectors, of course, I meant. So electro-optical devices which you can also deflect.
Yeah, we did consider this, and I'm blanking on the reason why we thought that they wouldn't work. But let me refresh my memory, and maybe we can talk later. Yeah.
Yeah.
There's time. So I'm not super familiar with the host selections that you do, but it seems to me that when you do like mostly spin up and mostly spin up, and you select those, you're breaking the SU2 symmetry. So is it essentially how much should we worry about ignoring quantum fluctuations? Or when you post select only specific number of particles, then you're ignoring the charge fluctuations?
Yeah, that's a great question. So in this case where we post-selected only for the spin-ups and completely ignore the spin-downs, of course, we recognize that we are likely in a spin imbalance system, but then our theory, our theoretical modeling, how we extract all of our temperatures and entropies also takes into account that the spin-downs have a few holes. So yeah, you're absolutely right to make that point. And another point, when we do the full spin post-selection, ups and downs, this is kind of safe, and we don't consider this cheating because we're not selecting on any correlations, right? We're just selecting on population. We know that in a conservative system, if you started with 4 ups, you should end with 4 ups. We're not throwing away any data based on where they are in the array, just purely the population. Of course, when I mentioned we did this SSH study, when we did the pi/2 RF spin flip to measure the XX correlations, then we can no longer post-select on 4 spin-ups and 4 spin-downs. There because after a spin flip, this magnetization is not conserved. So there, our only post-selection is to select for 8 atoms total, regardless of the spin component.
Following up on Alex' question, already in a 4-site cluster, 2x2, you can study Nagaoka transition with atoms in one half state. But then you will have to compare states with different values of the square. Right? Because if you just prepare spin 3 half and 1 half, they will not talk to each other. You can do it with a gradient of magnetic field. So is it something that you guys can do? Like gradient of magnetic field and tune and see how you go from 3 half ground state to 1 half ground state.
Yeah, I remember when you gave a talk at Princeton, you mentioned this already. A high magnetic gradient is kind of technically tricky for us because we work at very high magnetic fields, and to put a strong gradient on top of a 600 Gauss magnetic field is not possible given our current experiment.
Prepare 3 fermions in a placket is good.
Yes.
So just one has to think about how to connect.
Yes. Yeah.
I guess in your time we should move on. So let's then